Hi everyone, thank you so much for taking a time to watch my presentations today. I would like to share a topic of solar concentrator for electroconversions of carbon dioxide to solid carbons. Before I start, I would like to thank UMS and the organizing committee for giving me a chance to present in this conference. And I also like to thank all my co-researchers. In my presentations, I will firstly introduce the electroconversions of carbon dioxide to solid carbons, and thereafter the introductions of solar concentrator. I will explain the designs of solar concentrator that we have developed here in FKJ UMS, and then I will explain how we do the trial runs and also the outcomes of the solar concentrator and also the electrolysis process. Finally, I will conclude my presentations. The conversions of carbon dioxide to solid carbons can be carried out using the electrolysis in carbonate-based molten salts. I'm sure that everyone's remember how the electrolysis of waters is working. When voltage is applied on the pair of electrodes, what happens is the waters will split into hydrogen and oxygen. So we use the same concept in the electroconversions of carbon dioxide to solid carbons. However, the molten salts containing carbonate salts is being used. As you can see from this figure, when the compound is heated and melted, the molecules become ions. So in molten states, ions are mobiles, and ions can donate or receive electrons. The examples of carbonate salts that can be used is sodium carbonate and lithium carbonate. In molten states, the sodium carbonates and lithium carbonates become ions, and when voltage is applied, the ions can donate or receive electrons. Here I will explain how the carbon dioxide is being converted to solid carbons. There are three main reactions that occur during the conversions of carbon dioxide to solid carbons. As you can see from this figure, the electrons is moving from cathodes to anodes. So the reductions of carbonates at the cathodes occur, where the CO3 to negative will receive 4 electrons and produce carbons on the surface of the cathodes. Very often the carbons is deposited on the surface of the cathodes. At the same time, the oxidations of metal alkali or earth metal alkalides are forming oxides compounds in the moltens, and the oxides compounds will react with the purged carbon dioxides to form a carbonate compound. As long as the carbon dioxide is available, the three reactions that I have explained earlier can continuously occur. The carbons that has been converted from carbon dioxide tend to attach to the cathodes. This is one of the examples of carbons attached to the cathodes. Solar concentrator is the array of mirrors which used to reflect incident lights from the sunlight into the single points. It can magnify the power of the sun, which can generate an intense amounts of heat. The three figures shown in this slides shows the applications of solar concentrator, where the first picture shows a large-scale solar concentrator to generate steams for power generations and industrial process. The second one is the smaller solar concentrator, which usually used for domestic. This is to heat the water, and the third one is to do cooking. Now I would like to explain the designs of solar concentrator which we have developed in the FKJ. The solar concentrator designs is divided into three main parts. The first one is the parabolic dish and reflective material. The second one is the receiver, and the last one is the Fresnel lens configurations. We look at the first one, which is the parabolic dish and reflective material. The figure shown here is the examples of the assembled parabolic dish and reflective materials that we have developed in FKJ. So the functions of this parabolic dish and reflective material is to concentrate the incident lights to the single point. One of the important things that we have considered during the designing of the parabolic dish is to find the focal points of the parabolic dish. So we can use two formulas which is shown in this figure, which is the focal points is indicated by equations number 1 and equations number 2, where the d is actually the distance from this point to this point, and h is the depth of the parabolic dish. As for the reflective materials, we select a silver glass mirror due to its high reflective performance, which is more than 91%. The second part of the solar concentrator is the receiver. The receiver is placed on the focal points of the parabolic dish. It consists of electrolysis reactor and also the Fresnel lens configurations. But in these presentations, I will explain in more detail in part 3 for the Fresnel lens configurations. We look at the first part, which is the electrolysis reactor. The schematic diagrams of the reactor is shown in this figure. The reactor consists of crucible containing molten salts and two electrodes that have been submerged inside the molten salts. Both electrodes is being connected to the power supply to allow electrons moving from cathode to anode. At the top of the reactor, there is a reactor lid with hole that allow the carbon dioxide to push in and out from the system. There is a hole on the lids that allow thermocouples to be inserted so that the molten salt's temperature can be monitored throughout the experiments. To get the optimum radiations, the angle of parabolic dish was adjusted to a certain angle. One thing that we have considered in this design was the electrode must always immerse inside the molten salts. For example here, the initial setup is when the parabolic dish is placed facing vertically upwards. When the parabolic dish is adjusted, it is important to make sure that the molten salts inside the reactor is not flowing out and both electrodes is still immersed inside the molten salts. Now we look at the third part of the solar concentrator, which is the Fresnel lens configurations. The functions of the Fresnel lens is to change the intensity of heat at the receiver. Before I show you the configurations of Fresnel lenses, we look at the structure of this lens. So basically, Fresnel lens functions as a convex lens. However, this lens is thinner than the convex lens. Fresnel lens has a flat surface on one side, while facets on the other side. The Fresnel lenses arrangements is as shown here in this figure. There are two lenses with the facets facing to each other. So one Fresnel lenses is fixed and one lenses is movable. The lens can be moved to change the intensity on the receiver surface. In this figure, the schematic diagram and photo of the Fresnel lens configurations is shown. You can see that the radiations from the parabolic dish move from the fixed lens to the movable lens before it reaching the receiver. Now we move on to the tri-runs and the outputs of the tri-runs. The tri-runs was carried out by adjusting the parabolic dish at a certain angle so that we can get the optimum sun radiations. And then we adjust the two Fresnel lenses so that we can get the heat intensity. And then in number 3, we wait for the salts to melt completely before we can do the electrolysis process. The electrolysis process is initiated by draining the battery that has been pre-charged. Let's have a look on the outcomes of the test runs. The first one is the solar concentrator. It successfully projected heat to the receiver and managed to increase the temperatures of the molten salts to above 500 degrees Celsius without the presence of electricity. The molten salt's temperature can be maintained by adjusting the Fresnel lens distance. The limitations of the solar concentrator, however, is because of the thermal efficiency is very low, which is 36%. As for the electrolysis process, solid carbons are deposited on the cathodes. Therefore, we say that the carbon dioxide is successfully converted into solid carbons. The periods of charge draining is between 15 to 17 minutes, which is very fast. And with the charge of 6100 coulombs, carbon's weights of 0.44 grams can be obtained. The current efficiency is more than 100%, this due to the catalytic effect. Comparing the carbons that being produced using the solar concentrator to the carbons which is produced in the lab, we found out that the purity is similar and also the carbon structures is also similar. As a conclusion, the parabolic disc and the Francis lens configurations works well in melting the molten salts. The electrolysis process by draining the fully charged 17Ah battery successfully convert the absorbed carbon dioxide to 0.44 grams of solid carbons within the 15 to 17 minutes. Well, I think we have come to the end of my presentations. Once again, I would like to thank everyone for giving your time to watch my presentations. I hope you enjoy it.